Hello and welcome to Yageo Group Design It Day Automotive. Today's topic is high voltage isolation. My name is John Gallagher, Global Marketing Manager at Pulse Electronics, and I'm your host for today's presentation. Thank you for joining us here today as we discuss high voltage isolation. The presenter today is David Wiest, Product Marketing Engineer at Pulse Electronics. Before we start our presentation, I have some important information for you. The duration of this presentation is 30 minutes and has been pre-recorded. If you have questions on anything you see, we want to hear from you. Please go to go.chemet.com/did-contact. I have put this in the chat for reference. Please note the slide number to which your question is related if possible. We will follow up with your question after the event is over. Finally, when Design It Day is over, you will receive via email a short survey. Your feedback helps us to improve on future events. With this information, I hand it over to David. Hello, David, and thank you for your time today. David, please tell us a little bit about yourself before you start your webinar.
Hello, everybody. My name is David Wiest. I'm a field applications engineer for the power group within Pulse Electronics. I've been with the group since 2018. My support is focused on magnetics for discrete power supplies. That includes common mode chokes, high frequency current sense transformers, power inductors, gate drive transformers, and switch mode transformers. We support all markets, including automotive, the industrial market, telecom and communications, as well as the computing industry. Today, we're going to talk about isolation magnetics and how they relate to high voltage and low voltage electronics. Those are relative terms, and one may say that, well, the electronics are roughly designed the same, especially if you consider the magnetics. There is also going to be talk about safety and the safety of magnetics, which becomes very important in high voltage electronics. We'll also talk about typical topologies found in high voltage systems, how they're used, and how you choose the correct magnetic. And then we'll finish up with open Q&A. Some examples of a high voltage system. You may find these in electric vehicles, be them pure battery electric vehicles or hybrids. You'll find them in motor drives, both in the electronic vehicle world and the industrial world. Energy storage systems, where there are large battery packs storing solar and renewable energy. You can also find these in industrial power supplies and PLCs, as well as in the 5G market. Some examples, some counterexamples as a low voltage system, for example, may be a PoE system, where typically you have roughly 48 volts. Now, one may say that, well, if you're designing a transformer, the physics is all the same. Flyback is a flyback. And this all goes back to Faraday's law and Lenz's law. You say, okay, this is my peak current, this is my saturation, my volt seconds, and go from there. Same thing with a push-pull transformer or a gate drive transformer. However, there is one key difference when you talk about a low voltage system versus a high voltage system. And that difference comes down to safety. Safety is very important, especially as you expose users to higher voltage systems, or that is to say that in every electric product, the user should be protected from shock. In a low voltage system, that may not be as prevalent, as dangerous. If you're talking about an 800 volt battery system, that becomes very, very important. Safety is a huge field, very, very many standards relating to different end products. Two notable standards that have recently been retired are the UL 6950, which pertains to information technology equipment, and the IEC or UL 665, which pertains to audiovisual equipment. Those standards, as modern systems grow, those lines have blurred and become very difficult for engineers to decipher which spec they should follow. A new standard has been born from that, the IEC 62368. So that's not just a merging of the two, it's a whole new standard relevant for both. However, for the case of a magnetics designer or just your run-of-the-mill design engineer, the practice is still the same. You determine your working voltages, you determine what safety distance you need from that and what high pot distance you need from that, and design your magnetics and systems to that. So the process is still very much the same. This is still very important to understand, so you can choose, again, your safety distances as well as your wire installations. And product safety is a huge field. There are engineers who dedicate their complete time to it. So certainly most of us get a good first pass, but it's very important to talk with a safety engineer if you're unsure. And here at Pulse, we do have safety engineers on staff that help us ensure our designs meet safety requirements needed by our customers. Do want to touch on some very common terms that are important to understand. The first being the clearance distance, the second bullet there. If you're talking about 2 points, be it a PCB trace, a pair of PCB traces, or 2 pins, say the primary and secondary on a transformer, the clearance distance is the shortest possible path between 2 points, or in other words, as the crow flies or line of sight. So if on a PCB, you can imagine this is simply the distance between 2 traces. The creepage distance is the shortest distance between 2 points over a surface. That means if there's a, say, cutout in a PCB or a notch in a transformer bobbin, that distance must be followed along the surface, and that can be seen if you follow, say, the pink line in the graphics on the right. This is also important to note and can be impacted by, or I should say, the distance required is impacted by the environment that the product is set in. So if an environment is expected to be dusty, possibly conductive dust, or in moisture sensitive environments, these distances become longer. That way there's no possible exposure between the two. The next is working voltage. The working voltage is the maximum voltage that a transformer will see during its operation. That is across the primary to the secondary or along the isolation boundary. And again, the working voltage is very important to understand as you relate it to be it a custom magnetic design or your PCB, because that directly feeds into those creepage and clearance distances. One very common misconception is that the creepage distance, if you're looking at, say, a transformer, you can simply say, okay, I need a 8 millimeter creepage distance or safety distance. Many engineers tend to say, okay, I see the pin distance and go with that. And that can lead to issues down the line when you go to, say, UL test or UL certify your product, and that may get flagged. The reason being is that you also have to consider that the core is made of conductive material with ferrite or iron in it. And this conductive path counts as 0 millimeters for the safety distance. So where you may get something that is, say, 23 millimeters apart from the pin distance, in reality, you may only have a few millimeters, say, going up the bobbin. And you have to get a little bit creative when you consider the distances. We'll talk more about that later. For example, look where the wire is terminated or stripped back if you're using a triple insulated wire, and you have to consider paths on the inside of the bobbin going up to the core on the inner legs, a few things that are like that. Here you can see that as opposed to the standard EFD bobbin, there's a notched and extended bobbin that can actually meet that 9 millimeters creepage distance. So in a high voltage system where safety is critical, this lets design engineers meet those distances by extending the pin length away from the bobbin, away from the core, I should say. And if you follow the yellow line, any path has to go up the bobbin wall through the notch and then back across to the core. So this significantly extends the distance using the same standard core. And this is a relatively new technique developed. Traditionally, the notch has not been there. Traditional extended bobbins are much longer and taller, so you take up much more space for a given size. These new bobbins, they do provide the same distance, same safety distances, and again, smaller sizes. There are 3 different types of installations that are good to be aware of, especially as it pertains to a high voltage system. Functional insulation is, in a high voltage system, probably the least common. Functional insulation in English really just means what is the bare minimum to make your product work. And this is typically a design done in just plain magnet wire. If you don't need a strong isolation boundary, this is what is used. This is often the cheapest result. However, there is the bare minimum for safety. Next step up is basic insulation. This does provide some protection. In the most high voltage systems, we do see these. And again, you have to know your working voltage, your environment, and the material groups that are used in the products themselves. This is considered a somewhat safe, well, I shouldn't say somewhat safe. This is considered a safe insulation under fault conditions. Next step up is probably the most common. This is a reinforced insulation. You may see it as that double square symbol. You'll see that in various electronics. That denotes that it is the safest possible insulation system that's recognized. This is both single and supplemental insulation. Or in other words, instead of a single nylon or Teflon tube, there may be 2 coatings. Here, the distances tend to be much longer for a given working distance. Wire insulations are much thicker, so it's a tougher design, but again, much safer. Next, we'll jump into some of the use cases. We'll start with a push-pull transformer. And the basic operation of a push-pull transformer is that a DC input voltage is attached to a cinder tap on the primary. And then typically a small driver IC for the low power, maybe a total controller IC and auxiliary circuit for higher power. But most cases we see low power circuits like this where the switches are integrated in the single chip. The driver IC will run at a fixed 50% duty cycle, which then drives current through the rectifier diodes on the secondary. These are typically unregulated, good for very low power, say in an isolated RS-232 interface or an isolated CAN interface. These are very popular in the automotive markets. The reason being that they're very small, they're low cost due to their low BOM count, and very simple to implement. Here they'll see a portfolio of some of our push-pull transformers available on the market. These transformers vary from functional insulation and no safety distances, typically the smallest parts, all the way up to reinforced insulation with 12 millimeters of creepage distance. These parts are all catalog parts and readily available. There are custom options available as well if needed. Some things to look out for when choosing a push-pull transformer. First and foremost, one has to consider safety. That's always the most important. So again, it's important to either understand the standards yourself or work with the safety engineer or with Pulse to help define that. The next most important options, 2A, B, and C, I should say, are you have to make sure that the part will perform as needed in the circuit. One thing to consider is that you don't saturate your core. Core saturation is very bad in this case where the inductance will go to 0. that can often be catastrophic and result in a damaged circuit. So very important to avoid that. The good news is this is relatively simple to calculate. You must know your input voltage, your switching frequency, and core and design parameters of the transformer. In a data sheet, typically a transformer vendor like Pulse will supply those information, the needed information in the data sheet. If not, you can reach out to your applications engineer and we're happy to help. Typically, you don't want to exceed 3,000 Gauss or 300 millitesla. That's typically the limit of a ferrite over temperature. And one important thing to note is that there's often, between even core vendors, transformer or magnetic vendors, and design engineers, there's a lot of confusion on peak RMS AC current, even if it's a bipolar or unipolar. There's a lot of terminology that can get confusing. So it's important, break it down to its base units and keep things very fundamental. And you can see there are good ways to keep that consistent and keep your transformer running smoothly. Next is core losses and copper losses. These are important to note just because there are often efficiency targets to meet. Core losses are somewhat more difficult to calculate, all mostly based off of empirical data. The most famous being core losses are more difficult to calculate, being mostly based off of empirical data. There's a widely known formula developed by Charles Steinmetz, who was an engineer who very much enjoyed the practicality of gathering data and using that to drive decisions. Core losses are very complicated and nonlinear. They depend highly on the frequency that you're running at, as well as the flux density itself. So there are typically guidelines in the data sheet for a given platform on how to calculate this. Additionally, copper losses are also known. There's Ohm's law, just the RMS current applied times the DCR. You must also consider AC loss in the winding, and that's not shown here. And again, that's something that we help with. Together, you must make sure that these losses will add together to be reasonable within your circuit. And it's also important to consider the temperature rise of a platform. And again, there are typically guidance in a data sheet that will help you with this. Next, we'll talk about a flyback transformer, another very common topology found in a high voltage system. These vary. These are typically a different use case than a push-pull transformer. Oftentimes, the flyback transformer is used to generate the low to medium voltage that's regulated. Flybacks also benefit from having a low bill of materials or low BOM count. One major benefit from the flyback is that you can have multiple secondary windings isolated to their own grounds, or secondary outputs isolated to their own grounds, simply by adding an additional winding on the secondary. So an easy way to generate additional power supplies. These are also usually fairly tightly regulated. An example, you may find flyback transformers used to generate local reference or local power supplies for IGBT gate drives used in motor supplies. Typically, the flyback, the operation is different than a push-pull transformer, which is a traditional feed-forward type transformer. The flyback actually conducts current in the primary when the switch is turned on, and the diode, due to the nature of the winding, blocks that energy from flowing in the secondary. This causes the energy to store in the core. And then when the switch turns off, that field reverses and then current will conduct. So the flyback will not conduct at the same time. Common use cases in the flyback, you'll see that in a high voltage system, usually we don't see a lot of functional installation. That's because the site is crossing a critical boundary, be it in an inverter, in a battery management board, or a PLC. Basic installation, oftentimes that's seen perhaps in a gate drive situation, as shown in the last slide, where a user probably won't be touching that part of the board, but it still needs to have some sort of installation. Very common is reinforced installation. Most flybacks I've worked on seem to be reinforced, usually with 8 or more millimeters of creepage distance. And again, that's due to largely being driven by the electric vehicle world with 400-volt systems. Traditionally, as mentioned earlier, large bobbins with extended flanges have been used to meet these safety distances. There are some new innovative ways that we can use to reduce those sizes and still meet safety distances that are required. When you're choosing your flyback transformer, there are, again, some things to consider. Again, safety is very important, similar to the push-pull. And depending on what is needed, that will impact the wire selection, be it a triple insulated wire or a functional or a enameled wire. Saturation, because the windings don't conduct at the same time and energy is stored in the core, rather than looking at the volt seconds, it is important to consider the peak current running through the primary winding in the transformer. So it's a slightly different calculation to get there, but the rules are still very much the same, where you don't want to exceed 3,000 Gauss in order to saturate your transformer. Core losses, again, are very important, modeled by the typical Steinmetz equation. And copper losses, again, are the same. One thing to note that in a flyback transformer, that proximity losses, while still good to look at, are less prevalent. And that's, again, because both windings don't conduct at the same time. However, those design practices that reduce proximity loss are good for reducing leakage. And leakage inductance is very good to control. And leakage inductance is important to minimize or control depending on the application. High leakage inductance can lead to lossy snubbers or radiated emissions problems. So a very important thing to watch. And again, the temperature rise of a given platform. So the losses are important to manage, and it's important to make sure that the ambient temperature plus the self-heating of the part, again, usually with guidance from the datasheet, doesn't exceed the maximum operating temperature. And if you look at a quick example of a safety bobbin, these are the same transformer or the same core, an EP13 core. One on the left is the standard bobbin, usually found in a low voltage system like PoE. This is usually functional insulation using just plain enameled magnet wire. Here you can see that the core sits very close to the pins. The bobbin isn't very tall. Because of this, it's almost impossible to meet high safety distances required in today's high voltage systems. If you look on the right, there's an extended bobbin. This is the same core, can be the same winding, maybe some adjustments to accommodate a thicker insulation like a TIW, triple insulated wire on the bobbin. The legs of the bobbin are highly extended, and this part was designed to meet 8 millimeters of safety distance. If a triple insulated wire used on both legs, then this platform is possibly up to 10 millimeters of safety distance. And again, that enables traditional cores, enabling better cost structures and simplified designs as opposed to some larger parts. And if we go back to revisit the EFD20, this is just a real case example found in, for example, an inverter. The original design called out an EFD20, and while it worked, it did not meet the required safety in the project. So an extended bobbin with that notch allows us to, again, use that same optimized design and still meet safety requirements while minimizing the impact on the layout. Last but not least, we'll talk about gate drive transformers. These are relatively simple. Again, they just feed energy through. So one gate drive IC may drive the primary winding, and depending on the polarity of the both secondaries, it's very common for one to drive the high side FET and then the other to drive the low side FET. So you can drive both switching elements with one transformer with some creative application circuit and with proper layout of the transformer. These are probably the most competitive, or in the most competitive market, just because there are also semiconductor solutions available for gate drivers. So largely it depends on the design engineer's preference, and then also one must consider the nuances of the application. One thing to consider is that usually in a complex system, there's more than one boundary or more than one magnetic crossing the same boundary. Therefore, it's very important to keep consistent with your magnetics, and usually a more in-depth engagement with your magnetics vendor is good, just to make sure, hey, you're not using a reinforced part, say across one piece of the isolation boundary, but a functional insulation on the other. That may get you in trouble down the road once you go to certify your product. Some examples of that, again, going back to the silicon carbide or GaN switching elements seen in today's automotive world. Seems to be a very common application. And again, there are many different solutions, so a fair evaluation should be done. The magnetics can often provide flexibility that a silicon solution can't provide, especially engaging with the magnetics engineers. You can modify your turns ratios, modify your distances, which will impact your application. In summary, even though the physics are the same for a high voltage magnetic and a low voltage magnetic, safety is so very important to consider. And even across that different applications, a one-size-fit-all magnetic does not exist. So please don't gloss over the magnetic in your design. They're very important. Oftentimes, engineers stick with what's tried and true. I know I do. And that's a very good thing to do. Lets you enable cost-effective product. Today's world, it's often very, very important to emphasize performance. And we at Pulse, we do like to think we're on the edge of performance. So please engage with us if you see something in the catalog that you like but isn't close. We're often working on new developments that are applicable to current parts or current designs that haven't been released to market yet. And that may often benefit a design engineer greatly. And then, of course, existing designs are iterative. If something is close to working but not quite, please reach out and we're happy to see what we can do. Thank you.